Hello students, welcome you all to next session regarding discussion on reaction turbines, a continued part. In the previous session, we have discussed regarding the analysis of reaction turbines, then the condition for a blade efficiency of a reaction turbine, reheat factor, and now we'll be discussing some of the numerical problems related to the reaction turbines. So if you have any queries, you can send me an email to these email IDs which are visible on the screen. You can see here. Also, you can send me an WhatsApp message also. Now, let us begin the session, students. We will be discussing some problems on reaction turbines. So the question, if you observe carefully, it has been clearly stated that there is a 20-stage Parson turbine which receives steam at 15 bar, 300 degrees Celsius, and along with this, a 20-stage Parson turbine receives steam at 15 bar, 300 degrees Celsius, and the steam leaves the turbine at 0.1 bar. The turbine has a stage efficiency of 80% and the reheat factor is 1.06. The total power developed by the turbine is 10,658 kilowatt. Find the steam flow rate through the turbine, assuming all stages develop equal power. So in the previous session, we have discussed regarding the stage efficiency, the overall efficiency. So with respect to that, this particular question is being asked here. So students, already I have told you some of the things when they are given in the question. Please abstract the given data from the given question. So as I said, the initial point is, he has said that there is a 20-stage turbine, which means the number of stages are given as value is 20. Then always keep in mind, if the word reaction of the Parsons turbine is given, then the value of R is equal to 0.5. And when this is the case, you are having the conditions that is VR2 is equal to V1. Similarly, alpha 1 is equal to beta 2 and V2 is equal to VR1, which means alpha 2 is equal to beta 1. Then he says, this turbine, it is receiving steam at 15 bar and 300 degrees Celsius temperature. So means the pressure of the steam which is entering the turbine, it is at a pressure of 15 bar. Then temperature is 300 degrees Celsius, T1. And the steam leaves the turbine at a pressure of how much? 0.1 bar. That is, you can say this is the inlet pressure. The exit pressure is around, you can say 0.1 bar after passing all through 20 stages. Then he has said the turbine is the stage efficiency, eta S, stage efficiency is how much? 80%, that is 0.8. He has given the reheat factor value, that is RF is equal to 1.06. Then the total power developed by the turbine, total power he has given, that is PT, it is 10,658 kilowatt. Total power output 10,658 kilowatt. He had asked us to find out the steam flow rate. He has asked us to find out the steam flow rate, that is m dot. You need to find out here, assuming all the stages have developed the equal power. He has asked this question. Now students, when the question is asked on a steam turbine with the pressure and temperature values, then the thing you should very important notice, you should take the help of your modular chart here. So in the modular chart, you have to search for a 15 bar pressure line, 300 degrees Celsius temperature, where you will get the particular values. So just I will show you the things here. I have drawn a rough sketch in my slide where you will be able to understand how you can plot 15 bar pressure line and 300 degrees Celsius temperature in the graph chart. So initially, I have noted down this given data. Yes. So if this is your molar chart, students, already I have told you this is your molar chart. That is vertical axis is H, entropy, horizontal axis is S, that is H is enthalpy, or horizontal axis is S, that is entropy. So if you observe here in your chart, there will be this type of curved line. This line we call it as a saturation curve. And now for the given condition, according to the statement, that is 15 bar 300 degrees Celsius, in your molar chart, you should search for 15 bar pressure line, and on this 15 bar pressure line you should see where a temperature line of 300 degrees Celsius cuts. So wherever these two meet, that mark that is 0.1, and note down the value of enthalpy as I have shown here. You'll get the value of H1 at this particular point. Similarly, if you go for isentropic expansion, that is, if you move straight away downwards with the help of a pencil and scale in your molecular chart, if you move downwards, go on drawing a line until you meet a pressure of how much? 0.1 bar. There you will get the value of 2 dash. That is the thing, but your isentropic expansion, that is the value of H2 dash. Note the value of H2. These are the steps first you need to know. Once you get this one with the help of your stage efficiency of 80%, you can find out even the value of H2, and then the H2 value you should mark on where on this same pressure line, that is 0.1 bar. So somewhere it is moving upwards, here it is being located, and then corresponding enthalpy value you have to note it down, that is the value of H2. So now how to begin with the solution? Once you have plotted the points in the graph, you can go for the solution. As I said, from the molecular chart at 1 bar on 300, sorry, it should be of 15 bar. Make a correction, students. This I have forgot to make here a correction. I will make it a correction here. So as I said, for a pressure of 15 bar, I have made the correction, students. For a pressure of 15 bar 300 degrees Celsius, that is, if I move along the 15 bar pressure line and a temperature line of 300 degrees Celsius, at this point where the coincidence takes place, this is the value of one, that is H1. From the molecular chart, I have got its value as 3035 kilojoules per kg. Then moving downwards, if I go downwards, I will get the value of 2 dash at a pressure of how much? 0.1 bar. So now I have got the value of S2 dash is how much? That is 2200 kilojoules per kg. So now isentropic enthalpy drop is nothing but this is the value of isentropic enthalpy drop, students. That is the difference between H1 to S2 dash. That is H1 minus S2 dash will give you the isentropic enthalpy drop. So its value is around how much? 835 kilojoules per kg. So therefore, the overall efficiency of this particular turbine, where it is delta ST by delta ST dash, already the values are given to you. So we have the overall efficiency as the thing, but the product of stage efficiency into reheat factor. The stage efficiency is given to us. We need to find out the value of reheat factor. Now, the next step is also the reheat factor is given in the question to you. That is the value is 0.1.06. So through this, we can find out the value of the overall efficiency as 0.848. So once we have the overall efficiency, we can find out delta HT. That is using this previous equation, we'll get the value of delta HT as how much? 708.0 kilojoules per kg. Now, the enthalpy drop for per kg of a steam for each stage. We are having how many stages? 20 stages. So delta ST by N, that is the value of 708 by 08 by 20. If you divide for each stage, there is a drop of how much? It is having 35.404 kilojoules per kg. Similarly, total power is equal to m dot into delta HT. Total power is already given to us in the question, that is 10,658 kilowatt. Delta HT you have found out, its value is 708.08. So the mass flow rate you are going to get is how much? 15.051 kgs per second. Hope this point is clear to you all, students. Also, the same problem if you take out in another form, that is a stage of a turbine with Parsons blading delivers dry saturated steam at a speed of blade speeds of 90 meters per second. The mean blade is 40 mm and the blade moving exit angle is 20 degree. The blade moving exit angle is 20 degree. The axial velocity of the steam, he has said the axial velocity of the steam is how much? It is 3/4 of the blade velocity at mean radius. Steam is supplied to the stage at the rate of 9000 kg per hour. The effect of the blade thickness on the annulus area is, it has to be neglected. We should calculate the wheel speed, diagram efficiency, diagram power, enthalpy drop of steam in this particular stage. So now, as I was saying the things, if we take the analysis in this portion, first he has said Parsons spreading, which means it is a reaction turbine, that is R is equal to 0.5. This point is clear to us right now. Then he has said that there is a dry saturated steam at 2.7 bar. Dry saturated steam, that is the entry level of the pressure is how much? It is inlet pressure inlet PI. It is 2.7 bars. Then he has told that it is a dry saturated means X value is equal to 1, which means the value of this pressure line, it has to meet the saturation curve exactly. Then he has given us the value that the fixed blades at a velocity of 90 meters per second, means the value of V1 is already given in the question to us, that is 90 meters per second. Then he has said the mean blade height, that is the height of the blade, HM, it is equal to 40 mm. HM value is equal to 40 mm, that is 0.04 meters, the conversion. The moving blade exit angle, so moving blade is nothing but beta, as it is exit angle, it becomes beta 2, which is equal to 20 degrees. And in the reaction turbines, you know, beta 2 is equal to alpha 1. Then he says axial velocity of the steam, that is Vf, axial velocity of the steam, it is 3/4 of the blade velocity, that is 3/4 of the blade velocity, that is U. Then you need to find out the steam is supplied to the stage at the rate of how much? 9,000 kg per second, that is the mass flow rate he has given us, it is 9,000 kg per hours. Convert this into kgs per second. You have to find out the wheel speed. The wheel speed you need to find out, that is the value of n. Then diagram efficiency, blade efficiency, both are the same, students. This is wheel speed n. Then diagram efficiency or blade efficiency, both are same. Diagram power is the power, enthalpy drop is the delta H naught. So these are things which he has asked us to find out in this problem. Where important point is there, students, when you go for the plotting of points here in the molar chart, this is your saturation curve. You are having a pressure line of 2 bar and a pressure line of 3 bar. You don't have 2.7. So with the help of pencil, you should see the spacing between these two pressure lines, and you have to draw a slight light line which takes the trend of nearly 3 bars. You can say, so somewhere you will get like this somewhere. So here at the saturation curve where it meets, we call it as a dry saturated. This is the value of H1. This is point number 1. And here only you need to find out even the another one parameter, that is the specific volume. So specific volume, if you observe in your charts, it will be in the form of dotted lines. So here I will be writing those values. V is equal to some values of meter cube per kg. So the same you need to note down from the molar chart. So now let us begin with the solution. As I said, pressure is dry bar 2.7 bar dry saturated. V1 is 90 meters per second. He has given the mean height. He has given the exit blade angle, which is equal to the inlet angle. Now the mass flow rate, converting into kgs per second, it becomes 2.5 kg per second. You need to find these things. As I have said, the speed, that is the U. You need to find out the U, tangential speed, then diagram efficiency, then the power as well as delta H naught. Now we need to draw first the velocity triangles of a reaction turbine with a common base. You can see this is the velocity triangle. This is a combined velocity triangles. You can see these are the combined velocity triangles, inlet and outlet together for a reaction turbine. Then this is the thing, but a view of a ring itself having mean diameter dm. You can see this is that value mean diameter which they have marked here in the sketch also. This is dm. Now what we need to find out is using the analytical method for this particular problem, that is inlet velocity triangle with an angle of sin alpha 1, because as alpha 1 is given to us in the question itself. So this particular triangle beta 2 is given to us. Beta 2 is equal to alpha 1 from the property of the reaction turbines. So I can write this as sin alpha is equal to Vf by V1. So V1 is given to us. So alpha 1 you need to substitute here. Please make a correction here, students. This should be sine alpha 1. Huh? I have forgot. This should be sine alpha 1. So therefore, Vf is equal to V1 sine alpha 1. So we have the value of V1 sine alpha 1 is 20 degrees. So on substitution, we get 30.781 meters per second. Similarly, once we have this equation which is given in the question already, even this relation is given to us, that is the axial flow velocity is 3/4 of tangential speed. You will get the value of the wheel speed or the tangential speed using this equation, that is u is equal to 41.04133 meters per second. Then go for finding delta VU, that is VU is equal to VU1 plus VU2, where delta VU is equal to V1 cos alpha 1 plus V2 cos alpha 2, or this particular value of V2 cos alpha 2, I can write it in the form as already I have discussed in the previous sessions also, how we can write it as VR2 cos beta 2 minus U. Now, once we have this one, you can simplify as V1 cos alpha 1 minus U, or 2 V1 cos alpha 1 minus U. V1 value is given to us, alpha 1 is given to us, U just have calculated. So the value of delta VU, we get it as 128.103 meters per second. To find the mass flow rate, you know the equation. We are using m dot rho f AF into velocity of flow. So velocity of flow, it is already given, you have calculated. So you can find out the value of density of the fluid. Then you need to find out even the mass flow rate. So density of the fluid, to calculate this rho f, we need to take the help of the molar chart. So from the molar chart, at a pressure of 2.7 bar dry saturated, we have got the value of V1 as how much? That is 0.665 meter cube per kg. That is specific volume it is. So yes, as I said, in the molar chart, we have pressure lines of 2 bar and 3 bar. They are available with us. 2.7 bar is not available. So what you have to do is, with the help of pencil between these two curves, you have to follow the trend nearer to 3 bars. And wherever it meets the saturation curve, that is your 0.1. And between these two pressure lines, there will be dotted lines which you can see here in the figure. These are nothing but they are representing the specific volumes. They has written on those curves also in terms of meter cube per kg. So they are the values. So now, with an rough sketch and the using of the molar chart, I have got my V1 as specific volume as 0.665 meter cube kg. Why I have found out the specific volume is, here the reciprocal of specific volume is nothing but the density itself. So density you can calculate using this particular procedure. So therefore, the density of fluid is how much? It is 1.503 kg per meter cube. And if I substitute in the equation, mass flow rate is already given to us as 2.5 kg per second. So we get the area as 0.05403 meters square. So then next, using this particular equation, already the height of the mean blade height is given to us. You can find the diameter, that is AF is equal to pi into dm into h, where you can substitute the values except dm. All the values are available with us. The final value of dm, we get it as 0.4299 meters. So using your speed equation, that is u is equal to pi dm n by 60. So you can find out the value of n as how much? It is 1823.05 rpm. As the value of n, it should be a round number. We take it as approximately 1824 rpm. Then I go for my degree of reaction equation, which we have used previously in the previous sessions for the analysis purpose. I add it as the sum of the fixed blades and the moving blades, Vn squared by 2gc plus Vr2 square minus Vrn square by 2gc. I can again separate them, and what I will do here is, as we know the point that this Vr2 is equal to Vr1, I'll substitute this Vr2 as V1, you can see here. So if I sum up these together, I get it as only V1 square by Gc minus Vr1 square by Gc. Then from the velocity triangles, we have that value of Vr1 square is equal to V of 1 square plus V1 cos alpha 1 minus U. That is the velocity triangle which we have seen just now. So therefore, substitute the values, you get the value of Vr1. Then the energy, if you substitute the value of V1 and Vr1, the answer we get it as 6679.02 kilojoules per kg. Therefore, the diagram blade efficiency, how you can calculate? You can calculate as the ratio of work done to the energy available at the inlet. So already you know delta V, you know, yeah, we have found out. So the blade efficiency is 78.71%. Similarly, power m dot W, m dot U delta VU by GC. Here he has to find out per stage. So on substitution, we get it as 13.143 kilowatt. Similarly, enthalpy drop, enthalpy for fixed plates as well as for the moving plates, we take them together. That is V1 square minus V2 square by 2GC plus VR2 square minus VRN square by 2GC. It becomes V1 square minus V2 square by GC itself only, as we know the property for the reaction turbines, that is V1 is equal to VR2. So you replace V1 by VR2 or VR2 by V1. Similarly, V2 is equal to VR1, which means you can replace VR1 by V2, you get this equation. And on simplification, I get the value as 5258.041 kilojoules per kg. So these are some of the problems. These are some of the problems on the reaction turbines. So you can solve such kind of problems. If you have any queries, you can send me an email also. Thank you, students.